I'm okay.
So today we're gonna go through chapter 5, support vector machine. So I'm excited about that chapter. I think it's short enough that we should be able to go through it today. I know there's a lot of math, but again, I said, please do not let the math intimidate you, because actually the book we're supposed to be reading before we diverted to this book is how to get, how to do deep learning without a PhD, okay? So if that's the case, then you should not be intimidated. I just ask that you just keep the course. Last time, this was mainly for Chima, he was asking about decision boundaries, okay? And this is, the decision boundary tells us what our classifier will predict for any value of X. Whether, so in this image, it predicts that the blue class, the rounds are in the blue shaded area, and the red class is in the red shaded area. And so the line that divides in between these two things is called a decision boundary. It's super important for understanding support vector machines. So another example, right? So you have this, and if you hear Imon speaking during the lab meeting, she'll say the feature space, right? And here you're classifying things that look alike. So like dots, this type of wavy lines that are going downwards or something. You're trying to classify or null lines. You're trying to group all those things into a similar category. And so the lines that divide these categories are the decision boundaries. So, and obviously for Tim, I put it for him a special map of Africa here to understand that if it's Nigeria, it has a boundary from Kenya and these other places, because we're all very different. But he'll not get the joke because he decided not to feel well today. So I wanted to talk a little bit about strategy. And here are some things that you should be doing or should have done. So Twitter is a very, very good resource. And I encourage you to create a Twitter account. It's a good way to connect to others. It's a good way to find a curated list for reading. And hopefully after the elections, it's not, hopefully the people you follow are not too political so that you're only reading election stuff, but I find it a very, very good resource to keep me updated. And the reason is that we have to move away from now just reading before the lecture. I think you need to set aside maybe 30 minutes every day to just do something. And if you do this, I promise you that you will see tremendous gain, because you haven't realized it because you're just following the book. But if you start exploring your horizons, the lab meeting discussions, all those things should be expanding. And so for the, this is for Toby, Nazanin, then, the non-medics especially. I consider you on the medical side, Abby. You have to have a LinkedIn profile, right? So all these companies recruit through LinkedIn, and I don't really use mine, but you absolutely have to have it, because this is how people will know what you're doing. And so for the medical side, I say this is looks a little vain because I'm showing my search when you search for Google, but people in medicine will, like the doctor grades, the Yelp grades, they'll come up and put their story of what they think you are. So by having these profiles, including a Google Scholar one, which tracks your citations, and you have to just go, and if you have a Gmail, it's very easy, and I actually really use it a lot, is that all these things I sort of control a little bit of the messaging that gets out. And so if you look at the whole first page, okay? So these are some of the things that we should be doing. I talked about blogging, and it's super important now because what we should be doing is experimenting. So this week I worked on a data set, just passively, when I'm watching TV or something. And the beauty of doing machine learning now is that there's so many, we're using Google Colab, so you're not setting your computer from scratch. Most of the things you can do a little bit with on Colab or on a Kaggle notebook. And so you could simply just be reading through the the notebook of someone else, but I want you to start picking things from there. And so I found myself editing my notebook with some new resources and some new tricks that I found. I'm going to share it sometime, but I'm starting to build my clean notebook that I can pick any task and work on, because I never used to use scikit-learn for any of my machine learning projects before this book. But at the same time, when you do not understand something and you search for it and it's not well explained, that's your time to write it up. And once you write it up, then you post it on your LinkedIn and Twitter profile. Okay, so this has to be a strategy that, you know, I need to see a little more action. So we're making progress. I just put this here. You know, this should be very familiar: linear regression, housing prices, numbers. Logistic regression, when you're just trying to predict a class, right? We haven't done, you know, reinforcement learning, decision trees, naive Bayes, or a random forest. But today we are at support vector machines. And so as we start to gain these new places, you do need to keep very good notes. Trust me on this. And then you need to explore what other people, just this idea of repetition really improves learning. And so in my search, really, and this came via Twitter again, you can see Amazon Web Services released their machine learning university. And this is from September, so this is pretty new. I would never have found it. So I really, in fact, I use YouTube a lot, so much that I actually pay to not see the adverts, you know. And you know, and you can see that if I'm driving or if I'm just walking, you know, I can listen to, this is what I do when I'm not walking with anyone, like for a hike. I start to play these things to just start to hear them, because all these things we should be able to like listen in, and you'll be like, oh, I know what that means. I know what underfitting overfitting model evaluation means. I know what scikit-learn says about processing. And so don't forget, we also upload the the YouTube recordings, rather our recordings, because they're too big to be just put on Slack. And so this is the point of immersion. And if you don't do this, you're not going, now you've learned so many things, but you have to sort of get into the practice mode where you're trying, you're learning something, you're either listening to something, listening to a podcast, or reading a paper, or writing a blog post, and, you know, or watching another course, you know, passively. This is the Google one. Uh, which also is very, very embedded. And you know, because you know now to not be so overwhelmed when you see math or something like that, and you can understand, okay, this is the problem that's going to be done. And more importantly, you get a chance to look at the data. And when you have a chance to look at the data, you can start to understand some of the patterns that you see. So I mean, I had a really good example. I'll see if I can pull it up, but it was fantastic just to even, and it was something that we are doing more of, but I was looking through the data that I was analyzing, and I wrote my code, and it was very messy. And these guys wrote like 3 lines of code. It was beautiful. It did everything that I wanted. And so that I migrated it to my own code because of that. And so I cannot overemphasize this idea that we are a team here and we need to work together. And this is the way there's so much noise and so much overwhelming stuff out there. Hopefully by participating in this course, that's the barrier is going down. But remember, if Judy finds something nice, then I can post it. If, you know, Toby finds something nice, they can post it. And by sort of this community working together is how we can make sure we're all learning, or you find a good notebook or something like that. And so we need to use this channel, which is what we normally use for book club, to make sure that, you know, we are sharing resources, we are asking for help, we are working on other things and keeping the conversation and allowing other people to spend even 20 or 30 minutes every day studying. So I don't know that, let me see if I can just pull that up in 1 second if possible. May not work. know I'm not sharing right now, but so yesterday I ended up passively just watching this course for Amazon SageMaker, because these companies give quite a bit of let me change what I'm sharing. They give quite a bit. They deploy a lot of machine learning, like every so many minutes. And so and so this was a part of the just the task to do. And it's a churn prediction problem. They have this data set churn, and this just says, could you predict by looking at the data of a mobile phone services and the patterns of calling, who's going to be a customer or who's going to like not renew their mobile subscription. Okay. And this is a very common command that I learned from this book that I use now, right? We've talked about this churn info. I can tell that they're non-null values, and I can see, when they're objects, then I know those are categorical variables. When it's integer or float, those will be numbers. And so if I just did churn.describe, I'm going to get statistics. And so always we have to explore what this means. Actually, I'm the one who said churn.info because they had this to just describe. So this is the prediction value is a churn, whether the customer left the service true or false. It's a classification problem. And when what I liked best was this code that they put here. I wrote my code, I deleted it when I was cleaning my notebook, but this code here was just amazing. And the reason was they just did a cross tab, which I hadn't used before to look at my data. And what they're saying here is for every column, if you see the data type is an object, which I know is a categorical variable, then you should display a cross tabulation of that column and the percentage of observations. And you can see here that these are states, and it's saying, look, this is the percentage observations, okay? So, and I don't have to write this for every categorical variable. It's just going to take all of them, and it's going to say these are the number of unique values in the column. So that already does that. And then when I say churn.describe, then I know that it's going to just describe, the count, mean, standard deviation, minimum, the 25, 50th, 75 percentile, and the maximum. And then it's going to draw the diagrams. And you remember last time we had looked at these things, but what I enjoyed was I asked myself, what am I seeing from this data? Okay. So you can see like like the phone task, I think, what was it, had too many numbers because every number is unique, and you know that that's not going to be of practical value. And you can see so these are primarily looking at the predictions here. So if you look at churn, which is the column that I know is for predicting what's the turnaround, I can see only, if it's true, only 14% of the, like 15% of the customers churn. So there is some class imbalance. And if you look at number of unique values here, which is 33, and this is the phone number, that's how you know that you're not going to have too many good data from this point of view. And then if you look at the numeric values, you want the Gaussian distribution, and you can see that the things that are not very well distributed, and remember last time we were looking at the scales, and then you'll see it's primarily the voicemail message, which is this one, which is one big thing here, and then some things here. So it's not like something continuous like that. And you can see the area code, which was here. And so this is pretty obvious. And so what they ended up doing again was to say, why don't you draw this, this this diagram, because we're going to have two values, whether the customer is going to churn true or false. And if you look here, what they end up doing is something using the cross tab, how we have these false and true. So these are the customers who churn, and now you're looking at them by state. And you can see this now starts to give you more insight into the data. Okay, and we're using the same code where you're just using the data types, and then I'm not writing every column. Now I spend more of my time trying to look at it. So you can see that the customers who churn usually have an international plan and will never rarely have a voicemail. Okay, and so you can start to look at the differences if the charts distribution look too different. You know, the overall pattern looks the same here, and this one has a bimodal peak, which is the daily minutes, and then also same thing here. And then, so this started to make me start to open my mind, because I looked at the data and then I looked at the comments that came up, and I was like, oh, okay, that makes sense. And you can see here, there's just the people who churn make more customer service calls, which kind of makes sense because they're unhappy. Okay. And so now from that, when I come here and read, like the channels are fairly evenly distributed geographically, more likely to have an international plan, and less likely to have a voicemail plan, and exhibit some bimodality in daily minutes, and have large number of customer service calls. I want to check my mind that my eye is focusing and able to analyze data this way, because we understand that the feature engineering is what determines our machine learning success. Now, my charts were not pretty, but I looked at this, which we've done before. If you look at the classification notebook, you can see how I'm plotting here using this. Sorry guys, I'm about to finish. The scatter matrix using churn here. And now all of a sudden I have all my information, and and their correlation. And so I can obviously see that this row here and this one has a difference. And so those two, they have essentially 100% correlation with each other. So these two, you should just drop them from your area, from your code. And this was area code, and essentially the phone number. And so you reduce that. And then I started to see another function where I would find these perfectly straight lines. And so I started to see, oh, this is day minutes. And we know that you have to look at the other one, the day minutes and the day charge. And so those two will almost cause your model to overfit. And so, because they're very highly correlated. So either they're, and so you just need to keep one, because it's going to provide the same pattern recognition. So that's what I learned from that. And the way they ended up doing, like using categorical data using this pandas library that I've used before, which is pd.getDummies, that, because everything, remember, in a categorical variable is going to come in and be zeros or one. But that was the one hot encoding, which we really haven't used beyond that class, but is there. And so you can see that, all this other stuff is for how to deploy it on Amazon Cloud and train it, which is not pretty much relevant right now. But in this process, I solidified my knowledge from previous. And then when I see this and I see NumPy split in your train, validation, and test data, I remember that if I run this code again, I'll have a different result today. And so that you should be using, so I will rewrite this code in a new, just make a copy and start to use the test train split and figure out are there categories that need to be rationed so that I can do a stratified split and then train my model and see if I get the same result. So this was just very passive for me. I just looked at something different, and I tried to walk through the problem as I correlated to what I've learned. And so I just wanted to give something like that, and it would be great as we move forward if we spend like maybe 5 minutes where we have two people present and walk through a problem that they solved and what they learned. Okay, so Elmira, time to shine. Any comments, questions about what I said?
That was great. Like you started with like great mentorship points and like awesome. Like I enjoyed it.
I also enjoyed it.
You have to enjoy it, Toby.
Yeah, it was good to see, especially that part about immersion. I feel like I need to get to do that more, because I opened the tasted, I think that's the Titanic, but I still started doing it yet. I'm like, oh, do I jump in? Do I wait? But I'm gonna do it.
Yes, yes, absolutely. This is the only way we're going to get better. And if people do a little bit of this every time, so like just pick something, or even if it's just something, a better explanation you found, you know, um, come back and just show it. I'm telling you, this is crowd learning. You'll be surprised at how much, even I was surprised at how much I've learned, and how much when I'm reading, it could be even just reading a paper and you could say, this is what I learned, and something new.
Actually, that happened to me this week. I think I was reading an article about, I forgot what it was, but they talked about like area under the curve
Uh-huh.
data, and I was like, oh my gosh, I know that.
Yeah, exactly.
Yeah.
Okay, I don't want to steal your thunder. I know this is going to be great, so I'm quiet and muted.
All right, so you can see my screen and my mouse. Everything okay?
Yes.
All right, sounds good.
Yeah.
So chapter 5, we gone through, before we gone through regression and stuff, we talked about the map behind the regression models, and now we're gonna talk about the support vector machines, which are, let's see where they fit exactly. So, so this is the learning, machine learning. It's gonna be super obvious to you, but stating the obvious, it's under supervised. You can have classification or regression tasks. Before, in this book taught us how to do linear regression, polynomial regression for regression tasks. And obviously this one was for linear data distribution, and this one was for nonlinear data distribution. And then he also used regression models of logistic regression and softmax to do classification problems. And then the logistic regression was between the two classes, and softmax when we had multiple classes, and that was the problem that we wanted to solve. So as is in regression, we have linear and nonlinear problems. The same thing for classification. We have linear and nonlinear problems. Now, so where does support vector machines fit is, so this is like a set of models, or like one model that has functionality of doing regression tasks and classification tasks, and can do linear and nonlinear. It can handle linear and nonlinear data. So just these are, again, obvious to you, but I feel like I need to understand what's happening on regression tasks. Our goal is to predict a number based on some numbers or like features, whatever. So, and that task can be linear like this one, or can be nonlinear. This is a simple line, and A is like slope of this line, and B is where it intersects with Y. So this is like a line that we know. So he, for regression previously, he used a theta 1 as vector of our rate, the slope of that model, and then B's as like the bias term. And for nonlinear, so I just want, so if our data were just like this, so we could fit a quadratic function like this one to fit this fit into our data. So, and that was regression. For classification, again, we're dealing with linear and nonlinear ones. So this is a linear classification task when we want to like classify this moons and stars. And yes, I can put a line over here, and these are linearly classifiable. So, and but on these, you can see that I need to like put something nonlinear between these two classes to be able to separate them on this one and this one. So this one is just similar to this function. This is like a quadratic, and this one, I'm going to show you exactly how different degrees of polynomiality show on graphic views. And that this is like a 3-degree like cubic function, basically. Again, I'll get back to this later again. So just to recap, 1 degree polynomiality, basically no polynomiality is this one line as we had before on here. And then if we increase the degrees, these are the different things that we have. I have 5 of them. It can go up to like I don't know if there's any cap for that. So again, so this is the function that we use and all of these. So now, and then I also like
Can I ask you a question?
Yeah.
This is fantastic. What did you use to draw?
This one?
Uh-huh.
I have styled on my I use my iPad.
Oh, that's amazing.
Yeah.
That's
Yeah, and then I just so you can just use many like what I use is just I open up on my iPad, I open up a OneNote and then try to draw on it, and then I get a screenshot and like put it wherever I want. But I think there should be some apps that can do this, but because I'm comfortable with that, I didn't feel the need to like go search for those apps. But I do it on my iPad. All right.
Yeah, thank you.
Sure. So just not to feel lost, that these are for myself, to not to get lost in all of these data sets that he's presenting. So initially, so we are familiar with IRIS data set, MNIST, and also California housing prices. He introduced California housing prices in chapter 2 when he was going through the linear regression problem. He introduced MNIST for the first time when he, in chapter 3, when he was going through a linear classification problem. And in the last chapter, when he was trying to do multi-classes for like softmax regression, he introduced IRIS data set. So we know that these are like what these data sets are. And now on this chapter, he's also going to introduce a make moons data set. And it's what it is just creates some nonlinear classification data set. So two classes in a nonlinear form. So if I have that, so I can just go through the chapter. And this chapter is basically divided in 2 parts. First, he's going to talk about the SVM and how we can use a scikit-learn to like do this kind of model training. And then he is going to briefly spend some time to go under the math. Just this is not the same math that we learned on chapter 4 for regression. There we use that we defined our problem as a cost function of our line, and we try to minimize that. And that's like an optimization problem. And we had multiple solutions. One of them was just normal equation, like pseudo inversion. And the most powerful of them were gradient descent. We learned multiple of them, like stochastic gradient descent and like the rest of them. And but SVM may, although it's capable of using stochastic gradient descent also, but the math behind it is a little different that he's going to address it later on. So let's just also let me just show you if I go to scikit-learn, actually I have it open here. So this is the documentation in scikit-learn for support vector machines. And so you can see, so we talked about that. This support vector machines can be used for classification tasks or regression tasks. And for classification, there are some like modules or classes that scikit-learn has to offer. And he will be talking about all 4 of them: linear SVC, SVC with kernels. That kernel can be linear or can be polynomial or can be like some other different things like RBF. We will get into all of those. But so that's so you can always like access the actual things that are documented under the scikit-learn documentation. So going back here. Now I'm going to go to the book itself. And because now he's going to like talk about SVM and define it, and we'll do that using a linear classification example. For that, he is again showing us some the iris data set, which is this one. So he's showing two different like flower types, and you can just by visually, you can see that, yeah, I can just fit a line here to separate them. So, and he's defining SVM as a strategy to place a largest street between two classes, so in a way that not much of instances violate the margins of that street. So we have two goals here: the largest street with less violation, and this is something that will help us fine-tune our models later on. So obviously these are not such lines, and this is what it is. So this is what we want to achieve. And so SVM has its own characteristics. It's very sensitive to scaling. For example, if you have unscaled features, like this one is from 0 to 6 and this one is from 0 to 100, and you can see that you can, yes, you are able to fit a street over here between these blue and purples, but that's the street is narrow. You can do better if you scale them. So here you scale them and you can just fit a larger street between them. So if you're using SVM, we have to make sure that our model consists of some sort of a scaling. And yes, scikit-learn has this standard scalar feature that we, like functionality that we always use, so that will do it. So now he is going to tell us about a concept of soft and rigid margins. So let's just first talk about the rigid margins, and that is to say, okay, what was our goal? Our goal was to fit a street without violation. We are very super strict about that. So if our model sees such a data, like it's looking at it, where should I be putting that street to account for this outlier? It's impossible. It can't, because it's so rigid and we set the rules, so it can't do it. It's not going to be able to do that. If we move this outlier a little bit, like for example over here, it's going to be yes, now it's not impossible. Now it's going to be able to fit a small street over here, but it's very narrow. So one strategy to loosen up our model a little bit is to use a soft margin classification. And that's basically saying that how much are we trying to let this model put some of these instances, like let's some of our instances violate our street. And by the way, some very important, is something that doesn't make sense honestly, but something that it's important apparently in support vector machines is that these instances that are happening inside the street or at the margins of these are called support vectors. So whatever data you have outside of your street, this model doesn't care. The only thing that it cares is the data at or within the street. So that's like something important. So if you're adding more training data to your training pool, if those add to here, your model will not improve. But if any of those happen to be within the street, so that will make it that will change it. That will change the model. So that's another thing to remember. And so for, and then this, how we define our margins to be soft or rigid, there's a hyperparameter, and that is C. We will be using this hyperparameter no matter what task we're dealing with, classification or regression and whatever linearity it has. And so the lower the number of C, the more flexible our model is. So that's, more flexible our model is, and that what does that mean? It means that it's more generalizable to outside world. The more rigid we define our C, like the higher the number, it's gonna be, yes, it's gonna be fit to our data. It's not gonna let any instance to happen within that street, but it's less generalizable. So if our model is overfitting, so we can just loosen it up to like decrease the value of the C. So. Okay, now he is using again, he's gonna introduce these models, all of them. So for linear purposes, he is using the iris data set as we talked about, and he's gonna use a linear SVC and also SVC with linear kernels. So first, so these two he's gonna be using. So for this one, he's like, for linear classification, he's just importing all his modules. And this linear SVC is a subcategory of SVM, as we saw on the documentation over here. And again, he's loading his iris data set, defining the data and the target values to be in one of those types. I don't care which one it is. And so with two features of the petal length and the width. And then it will create a pipeline. Definitely it will do the standard scalar, we'll use that to scale our features. We are using SVM, remember? So, and then here it has two, hyperparameters. Like one of them is hyperparameter and the other one is the loss function. And both of them are very important. It's using as one, so it's just relatively flexible model. And it is using hinge as its loss function. We will talk exactly about what hinge is as opposed to RMSE before. So this is very important. If you're trying to train an SVM classifier, we have to use a linear SVM classifier. We have to use this loss function. Then we are training it in our data, and then he will show that how it's going to output a number, and that number is either 0 or 1. 1 meaning that it is positive for the class that we do, for the target, or 0 is if it's negative. It's not going to output the regression, like the probability that we had with regression models that we used for classification. And also you can. Also, he's using SVC. We can use SVC, which is not on, so it's under SVM. So it is a current, like it is another functionality. For that, when you put it over here, instead you have to like define your kernel. And because we're dealing with a linear task, we will define it as linear and see the same. But we don't, at this time, we don't need to define a loss function here. So.
One thing, Almira, I mean, this is great. And welcome, Leila, who's one of our new doctors joining in. And so one thing that I wanted to point out here is just a reminder of how scikit-learn, you remember the pipeline, right? We haven't gone back there yet, but this is a very good example of this, right? So where we see that import pipeline, import standard scalar, because you want everything in the same unit, and then what you're saying, the linear SVC, but you're presenting this, I mean, just perfect.
Awesome, thank you. All right, and so let me see. I didn't notice that Pri also joined us, and also.
Okay, so since you've slowed down, Leila, do you want to introduce yourself? If you can. I know you're in between.
Hi, good afternoon, everybody. My name is Leila. I am and clinical informatics fellow, interested in getting more experience in machine learning, and Judy was kind enough to include me in the group. Happy to join.
You get to know everyone. We have two people missing. Elmira will introduce themselves. Pri, how are you doing? It's been a while.
Yeah, I'm a bit sick, but I guess now I'm fine. So okay. I was skipping this meeting and I'm far behind you guys. I've just completed chapter 2, but I thought of joining and seeing what's going on, and I can exactly learn, and then I'll go through the book.
Okay. Yeah, you're the
well,
boss.
if I'm
yes.
Sorry,
if you're
no, nothing.
No. Get some lemon, Pri.
Yeah, I'm taking all those things.
Okay.
Just the vitamin C and the immunity boosting, but somehow I got a cold. and I don't know how. So I was just taking a break.
Okay. Well, get well soon. So Lela Pri is one of our very good students who lives in New Delhi, who's not feeling well right now. So,
All right. Also, I want to welcome Layla. I'm Almira. I'm a radiology resident, fourth-year radiology resident at the University of Illinois in Chicago. And again, like probably like yourself, Judy was also kind enough to let me in her group. So I'm also like interested in machine learning to understand that like from the basics. And so here we are. Okay. So any questions so far? All right. Just I interrupt everybody when they're talking, so please do interrupt me and then do ask questions or like give comments, feedbacks, whatever. All right. So we talked about on the chapter itself. I'm going down to all the ways that we can use SVM models, and we already talked about two of them, which was like linear SVC and SVC with kernel of linear kernel. Also, we can use, remember, stochastic gradient descent classifier from linear classifier of scikit-learn. So if we set the loss function of that classifier to hinge instead of RMSE that we originally set, and also if we set this hyperparameter, then what it will do is it's gonna train a linear SVM classifier for us. Why we even think about using this is that these two models, this one and this one, are not capable of doing out of core training. So if you're dealing with that situation, it's good to consider, but we will talk about which one to use first, and then what are the differences between these three ways of doing classification that we've learned so far. So this one first was introduced in chapter 3 with MNIST data set. So it used just some sort of gradient descent. But again, on that, there we use a different loss function. And now we are adding two more to our models to be able to classify things. All right, so I'm gonna go through the nonlinear problems, classification problems. For this one, we're gonna first start with like what are the strategies if you're having nonlinear classification problems. There are two ways. Either you can extract the polynomial features of your current features and then basically map it into a different dimension. And by doing that, you will have two options. Either you can use those parameters now. I'm not sure if those new features in a different dimension to feed into your linear SVC model, or you can use a SVC with polynomial kernel. Both of them are possible. So, and then there's another way of doing that, dealing with nonlinear classification problems is just extracting like similarity features, and we will talk more about that with like some examples on like this one that he's introducing. All right, so let's just focus on this one. This is an example of a polynomial, an example of nonlinear problem, that classification problem. We cannot fit a line to classify these blue and green dots. So, but if we introduce, so these are not separable on this one dimension. But what if we introduce a second dimension like this one, and that dimension, we define it as some sort of, it has some kind of a relationship with the initial dimension. And we are hoping that by doing that, by transforming in the second, like the additional dimension, we can spread these instances in such a way that we can fit a line between them. So you can see it over here. So this one, so basically we're looking from x2, a new feature, which happens to be the square of x1. So now we are seeing that we can fit this line to separate these. So, but last on this one, we were looking from x, not seeing x2 as the new dimension, but now we can see that on a different dimension, we can do that. So this is what polynomial features are. So how can we do it on scikit-learn? One way to do that, it's going to be linear SVC with polynomial feature, and I'll get to that. Again, MakeMoon, now he's introducing MakeMoon's data set. And again, as I said, what it is this is a documentation for MakeMoon data set. And as you can see, it's what it is just based on our definition. It's going to output some sort of nonlinear classes for us. Most of them are 2 classes, and I think it's 2 classes, yeah. So having that, so we are so here, first we're importing that data set, and then we're importing the pipeline, as Julie said, and then also from the pre-processing, we are importing the polynomial features. This is the same thing that we imported to be used for polynomial feature extraction for regression problems. So this is basically the same. Now, we are defining our data as MakeMoons, which we just imported, and we're defining that I'm gonna need only like 100 samples. So all these does adds up to 100, and like add some noise to it, and then here it is. So you can see that what it looks. So yes, just by looking at it, you're not going to be able to put a line in between to classify these two. So that makes us to use some polynomial, like one of those strategies that we discussed. Now we're using polynomial features, and we're defining as degree 3. Remember, I showed you let's see, on this one. So this was degree 1, this is degree 2, and this is degree 3. And it kind of makes sense if I go back. If I go back here, it kind of makes sense because it looks like this is, if I fit a cubic function over here, it can separate these classes for me. So that's why he's using degree of 3. So, and then again, he will definitely use a standardization. And then here, nothing has changed. Some sort of flexibility and has hinge as function again. So this is what it is. And then we are training it on our data. The other way of doing the same thing is to use an SVC and set the kernel instead of linear to poly. On this one, again, we need to put a degree of polynomiality also. I'm not even sure if polynomiality is a noun or not, but anyway. And then, so, one second, okay. So, and then on this one, again, because this is like kernel based, we don't need to use loss function. We don't need to use loss function. C is the same as before, some sort of flexibility of the margin, soft margin. And here's the coefficient. This is the first time that he's introducing this one. And this is another hyperparameter that is defining how much we want our model to be dependent on higher degrees that we are defining. So what do we mean by that? Again, this is the polynomial, the overall function, right? If we define our degree of polynomiality as 3, as in this case, 3. So these are like A's are basically the weights that we are, that previously we talked about as theta 1s. So these are the weights of that goes along with these higher degrees of X. So if I want to define that, hey, you know what? It's 3, so I'm going to have 2, 1, and x to the power of 0 here. If I use a higher number for coefficient, which also he's referring to as, just going to go there on this. here. So he's introducing coefficient and he's referring to that coefficient as R over here. So this is saying to the model that yes, I have defined some degrees, here 10 and here 3, but these are two separate ways of doing the same thing for him. But this is 3, and this is the line, the function for the 3 degrees of polynomiality. And this is, if we define 10 degrees, obviously this is more skewed. But this one, he's saying that by comparing R's in between these two, it is saying that, you know what, put more weight on the higher degrees, like x to the power of 10, whatever a comes with that, put more weight on that rather than something which has lesser degrees. That's basically another hyperparameters that you can just fine tune. And again, if you, the higher the degrees, the higher the degrees, more the more overfit, the more at risk your model is for overfitting. Because, and also, like, if you have more rigidity, like higher C's, and this one is the same, but if your hyperparameter C is high, if your degree is super high, and if your R or coefficient 0 is also high, all of them are saying that you just give me the best thing that can fit in this instances. And yes, it will give you that, but it's not going to be generalizable, and you're risking being doing the overfitting. So that's that. And then obviously he presented, he taught us before, but these are like, we're dealing with, on this SVM, we're dealing with lots of hyperparameters, and you don't know what would be the best. And then he's saying that just use a grid search that he introduced in chapter 2 for California housing data set. Just use that to like have an idea. On exercises, he's just actually using that. And if we have time, we'll go through those also. So now to the similarity features. Okay. The way he described it, I found it that may not be intuitive. So I thought about an example to how to, it should be two, forget about this one. All right, so I thought about an example of how to describe using similarity feature extraction to solving nonlinearity classification problems. So I thought if I was somebody at hotel reception, and my job was to listen to some people who were speaking in Spanish, and my job was to say, to classify them as Mexican or Spanish. And this is my task. The problem is I'm terrible at dialect, so it's very difficult for me. And this difficulty is in machine learning nomenclature. Is just not a different definition of nonlinearity. At least this is how I explain it to myself. So classifying them based on the dialect is difficult, so nonlinear. So how can I change it in a way that I can solve this problem based on what I know, which is linear to me? And so I'm good at geography, so I thought about this. I know that Spain and Mexico, both people from there, both speak Spanish. And these reds are their dialect, which their dialect features, and I have no clue what they are. One of the ways that I can actually do is to, instead of looking at their dialect, I put some landmarks in the world, that in the dimensions that I know in this world. I put some landmark in my data. For example, here I'm using United States and UK as my landmarks, and say, you know what? I know that Mexicans will be close to the United States and farther from UK. The other way is for the Spanish people from Spain. So if I use these, if I measure the distance, instead of dealing with red as dialect, which is a nonlinear thing, and I have no clue, I can use break it down for each of my tourists. I can define an XY, X1 and X2, and then I know that, and then I can easily calculate where they are, basically based on their distance. And so nobody will know that I have no clue about dialect, for example. So this is what he is doing, but this way. Yes, geography is easy for me, but Gaussian, bell-shaped Gaussian function is easy for computers. So that's why he is using a Gaussian function, bell-shaped function, and he's putting that on different areas in your data set. Again, we're dealing with the same one-dimensional data set, and these are spread like this. And our job is to classify classify green from blue. So we're putting two different landmarks, US, UK, and then we will go through each one of these instances in our training set, and we will see how far they are from these two landmarks. So, for example, he's putting arrow on this one. So this one, if I go up, it will intersect about like maybe 0.3 over here. So I know that the X3 feature would be that, and then X2 feature would be, if I go up, it's going to intersect somewhere over here, maybe like 0.6. And this is exactly it is. So somewhere over here, and it intersects somewhere over here. So then what we are doing is discarding the initial feature, and we are mapping it in a different dimension with completely different features. And remember, on the polynomial feature extraction, our new dimension is first of all, it's based on the first one, although, yeah, it's based on the first one, but we also, on the new dimension, we are also using the initial feature. But on this one, similarity extraction, similarity feature extraction, what we do, we just discard the X1, and then we will map it into a new dimension with two different features. And then we're hoping that by doing this, we will be able to separate them linearly. And that's what happened on this case. I guess, I don't know why, probably this is one of those mathematical functions that over time has been shown that it's very good at doing these kind of tasks. So that's why he's introducing this. But I don't know, like if you put like any sort of function here, if that would have done the same job or not. But in any case, so this is something that it's important to understand the concept, I guess. Yes, you can use, you can plug in your numbers into this formula and like get, or like I just use where they intersect with the plots and then got the numbers, as you can see here. And for doing that on scikit-learn, here it is, the same, basically the same pipeline, but here for kernel, we are using RBF as kernel. There's another hyperparameter, and that's gamma. We will talk about that. And again, our good old C, which is very, very soft here. And so we're allowing for lots of margin violation. And then we're fitting our data. Okay, so here's the result, and we're going to talk about the hyperparameters in that in this result. So first, let's talk. Talk about how C has changed our decision boundaries. So on the left side, we're having very delicate C, I would say. So this is a very soft margin. So it's letting lots of stuff to be misclassified. You can see lots of blue over here and lots of green over here, and like over here, some dots over here, and like some greens going to the wrong class. So this is that. But here, if you can see, with increasing the C, more rigid hyperparameter, it is causing more of these stuff to be classified in their where they should, basically, as you can see here. Now, look where there's yes, we thought there's another hyperparameter, and that's gamma. And like how that's going to change anything. So that's, again, on the upper part, this is gamma with a lower number, and this is a higher gamma. So the higher gamma, it's also will cause more, it's going to be make our model to include, be more sensitive to misclassification, meaning that it needs to include, it needs to include more and more data in the correct classes. Like for example, here it's gamma 1 and compared to this one, so basically these two lower to the upper part, this is also is prone to overfitting to our each instances. It's going to wiggle around all these data, and then that's not good. That's not well. If it's prone to overfit, so if you're overfitting, what you would do, you have to like drop the gamma and drop the C, like, and from here, go to this one to be more generalizable. Okay, so let me see. So we talked about similarity features, and we talked about how to do it with the RBF kernel, and we talked about all the hyperparameters. Now we are done with classification problems. We've gone through linear and nonlinear. So before starting anything else, is there any question? Everybody with me?
Yeah, okay. Thank you so much, Elmira. Hi, Leila. My name is Toby, and I'm a research intern at HITI, and I'm very grateful to Judy for bringing me on to this book club. Okay, so thanks, Amira. I've gained a lot from your awesome presentation, and I have two questions. The first is SGD. So on the slide, the author mentioned that when you make use of linear SVC, your results converges faster than SGD. But in chapter 3 or chapter 4, when we talked about SGD, we mentioned that with SGD, your results converges faster. So do you know why the linear SVC converges faster than the SGD?
So he is talking about like what these models are based on. There's different libraries that these models are based on. Let me just go here.
Also, Toby, if you remember the type of batch, right? So mini batch and whole dataset batch, right? You remember STD jumps around at the end till you regularize it. You either do the early stopping after it's not gaining any, if the errors are not improving after several epochs, right? And so it never really comes to the global minima until you do something about it. Do you remember that?
Yes, I do.
And so I wonder if that's also a little bit of why, you know, this matters this way, because the linear is almost like doing batch. The line, you'll just draw a line and you'll come to the end. But the SGD, you still have to, I don't know why, I don't think that's the reason, but I don't know that.
And then also I was thinking that, so based on what you were saying, Judy, if we change stochastic to some other format, like let's say mini batch, then we would have been able to converge better. So
I don't know, I didn't experiment with that. Yeah.
Yeah.
Toby will research on this and tell us. See, this is why you shouldn't ask questions, Toby, you know this.
Thanks, Toby, that was a great point too. And then also I'm thinking that, yes, this is like a good model to begin with, but maybe why he's just putting all of his bets on SVM is that maybe it's just better than this, for whatever reason, like fundamentally is better maybe. And like, although this is, and even though maybe even if we change the gradient descent classifiers to like mini batch or something, maybe it's not going to work better. We don't know, like as Judy said, we haven't experiment on that, but maybe fundamentally SVM is just better than the other classifiers that we've learned before. Abby, how do you feel?
I was thinking SVM, from what I understood from the chapter, is it on SVM is supposed to utilize, or rather like a lot of data sets and complicated ones, like it kind of makes it easier to, what do you call it, to create those models versus the SGD, no? I don't know. But anyways,
You should, no, I don't think, so you're correct, but you're merging two different things, right? So
okay.
the stochastic gradient descent, remember, is the example I told you guys about being on top of a hill, right? So machine learning, you're not giving the rules to how the program should be coded, right? So this is the difference from traditional programming to machine learning. So you're showing adequate samples of training data and then letting the model learn good habits. When it makes a mistake, you penalize it, right? But you need an algorithm that's going to track all those iterations, the hyperparameters, and the losses that the model is making, right? So that algorithm, that mathematical function that tracks what the model is doing with every run and whether it's coming close to the bottom of the hill from the top is the stochastic gradient descent, right? That's why it always has a direction, and you want to figure out the learning rate so that the steps that you're coming down the hill on are adequate. You're not taking very big steps, or you're not taking too few steps that you'll never converge to the bottom, right? So SGD is something you just have to understand, because when you go to deep learning models, it is a big, and people have different ways of optimizing, but always remember, this is how you get from the top of the hill to your target, okay? So here, I think, more when I read this, for me, I've never done any SVM, to be honest, till this chapter. And I actually spent some time reviewing other people's notes on it, is that what you want to do is figure out if you can find a way to linearly separate your data set, your classifier, right? Because it has to be two categories. Then what you will have to do is you either have to transform this using the polynomial features, just the way Amira said, or you're going to bring similarities, but you just have to figure out how you'll separate. Then you'll draw all possible straight lines through that data and figure out which one has the best fit with the widest margin that separates the two classes, like the best highway or something like that. And so for me, this was just that you could use this SGD. When I see this, like the SGD classifier, for me, this is more that you're relying on the mathematical function of how the model is tracking the process of training and the hyperparameters and how it comes to the global minima. But I'll spend some time on this and I'll have a better answer next time. Maybe you should ask no more questions. Pri, do you want to say something?
I have a doubt. Like, this SGD classifier same as that of the SGD optimizer we use?
Yeah, that's what he said in the book.
So in that case, I think that it will converge faster because, uh, like you explained the hill concept. So that should converge much more quickly than any other algorithm because it tries to find the minima as soon as possible and stabilize itself. Am I making sense? Like it's move
But
in the steps of learning rate. I'm relating with the deep models, but I think it should work in that way only.
Yeah. Okay.
just
That's an unsolved area. We'll have to go back again.
so just here it says that linear SVC, as is the stochastic gradient descent, are from liblinear library from scikit-learn. But the other one, the SVC class, is from a different one. So yeah, between these two, why this is one? So he is just saying that although you're saying that it has to be converged fast, he's clearly saying that it is not converging fast. And So he just said it doesn't converge as fast as linear as, well, maybe it's fast, but it's not as fast as linear SVC. And yeah, all right. So I'm gonna move on to a very brief subchapter, and that is computational complexity. So he introduced us SVM and linear SVC, SVC and linear SVC. And this one is the one that you can use kernels, and this is, you can just use it with a hinge loss function. And he already talked about this one before, and he's just saying that like how this one and this one are linearly their computational complexity is linearly proportional to it's linearly proportional to our instances. M is the number of instances, and N is the number of feature. So, but SVC on the other hand, the complexity of it, it goes non-linearly higher with the number of instances. So later on, he's going to describe that if you're dealing with very large data set with millions of features, you'd better off to use one of these rather than SVC with kernels if you have a choice, because otherwise you're going to end up with having a model that is very computationally complex because it is a function of M2 or like M3. Like that. All right, and then from these, the only one that we can use out of core is this one, the SEG classifier. All right, so I'm gonna move on to SVM regression. So by far we've talked about the classification one. Now let's move on to regression. So the definition of regression, the definition that SVM uses to do the regression is to the same street analogy, and then here, instead of the previous classification one that is trying to keep the street without any violator, here is the quite opposite. We want to have the largest street that is fitting in as much as instances that we have. On this one, there's a hyperparameter introduced, and that is epsilon, which is defining the width of the street. The higher, the larger the street. So, and then we don't so we don't care about whatever is inside the street, unlike the classification one. What we care about is whatever at the margin or outside of the street. So that's why this SVM for regression is epsilon insensitive. Now, how do we do that with scikit-learn? So first we can use like similar to the linear SVC for classifier, we can use linear SVR for regressor. And so we can import that from the scikit-learn, the same library, and then the hyperparameter is epsilon, and you can see if we change the epsilon, how that's gonna change the width of my classifier, basically the street. So that's that, and then there's another way to do that. If we were dealing with that was a linear one. If you're dealing with nonlinear data, so he's just presenting a data which you probably we're all recognizing that this is like a quadratic function. We can fit a quadratic function on this one, and if we use SVR as opposed to SVC that we had before, and use a kernel poly, but basically it's everything is going to be the same as before, but here we're using the kernel poly and degree to y2 because this is we know that this is like a x2 function, and that, again we have the same C. As I said, this is a hyperparameter that goes with SVM everywhere, and so this is like quite rigid than the previous ones that we had, and we have a epsilon over here, which is 0.1, meaning that a smaller caliber street. And then we'll fit that, and these are the results. Now at this point, we're done with how we can do SVM with scikit-learn. Now he's going to talk about the math under that. So maybe I can answer Abby's question with talking about how this one, the math under SVM is different than the math for regression. Although SVM is capable of using the same strategies mathematically that regression models use, but it has its own unique features as well. So, so first of all, what are we trying to do here? We have definitions. We want to, just gonna go to, actually, let's just stay here. So we have we're trying to fit a model, and that model is a function, and that function here is referred to as weight by x plus b. Previously, we talked about this as b as theta 0 on the regression models and w as theta 1 as vector of all the weights. But here is just changing it to, by convention, he's changing it to w and b, and he's not using the similar terms. So this is the function that he is going to use, and he's calling it decision function or like decision prediction, like the predictions. So what is the goal of SVM is to increase the largest street, right? And that in order to get to that level, for this one, we need to like think not linear. We need to think not in 2 dimension, but in like 3 dimension, because it is not, because it's a street, it's not a line, it's actually an area. So what it is doing is to crossing a new area, like a plane through the plane of our data set, like over here. So here, this is our, in this 2 dimension, like this one and this one, this is the dimension that we are familiar with our data here. So, and we know that they may not be separable in that 2 dimension. We may need to like include like some additional dimensions to be able to separate them. So SVM and this SVM fits a new plane with in a different dimension, in an additional dimension, and it crosses, and that hoping that that plane intersects from our plane in such a way that it will separate the intersection that separate our classes, like over here. So this is our data plane, and this is our decision plane. So, and then, so when these 2 planes intersect, this is where, by definition, this function is 0. And you can also like see over here, the 3rd dimension that we're introducing to our data plane is the decision. Let me put it over here. Is h, which is our function, and at 0, and you can see 0 is our data plane. At 0, it intersects with our data, right? So if it's positive, by definition, we are dealing with one class, and if it's negative, we are dealing with the other class. Okay, so this is like what we should be knowing. And and having that in mind, so he is just saying that. So our prediction is that we want 0, meaning that this is another class, not our desired class. If this function is negative, -0, it's the other class that we're not interested at, so we're giving it 0. Or if it's positive right here, if it this is in our desired class, the target class, and this will be output as 1. Okay, so having those in mind, just knowing that what lines and slopes do when they're projecting to a different line, we can compare these 2 graphs. One of them, so just assume that, so yeah, we talked about 3-dimensional over here, but let's just simplify, just only think about one cut of this 3-dimension on these 2 graphs. If this is the slope of our hyperplane, like the decision plane on our data plane, and if this is the slope, which is higher than this one, then it is intersecting with our data plane, it's going to be a smaller number, as opposed to this one, which is has lower slope, but it will project as a wider margin on our data plane. And this is nothing but the width of my street, because if you can see, this is the intersection, and based on the slope of this hyperplane over my data plane, that is the definition of the width of my street. And you can see it on these parallel lines that goes along the main intersection line. So what our goal is, if we want to do if we want to get the largest street, so basically what we want to do is to decrease this weight. So that's just based on these, is obvious. So my goal in SVM is to decrease this number. But we also have another goal, and that is not to let violators in my street. And how we can talk about that is by defining a new function, and I'll get to that actually on this one. So basically my strategy is boiled down on this one. If we want to be restricted, strictly have a rigid module that has a larger possible street, but with 0 violator, that's how it goes. First of all, as we discussed, we want to decrease our weight. Y is using, instead of like W, it's using like 1/2, transpose like W. And so because in the optimization problem, when he's going to solve this, he's going to use take the first derivative of this one. So this W and W is going to be W2, and then when it's going to bring it back, when you take derivatives, it's going to be here, so it's going to be W itself. So it's like a nice derivative. So that's why he's doing that. Or you can just think about it. You're minimizing weight, basically. That's it. Also, this is defining my width of the width of my street. But how to control for violators? Here it is. We're defining t as something which is negative. It's -1 for if my function is if my decision function outputs a negative number. What that will be is to -1 by something negative is going to be positive. Okay, and also we're defining this t as a positive one for the occasions that my model outputs a positive number. So +1 by positive is going to be a positive number. So that holds true. What do I mean? And then if it was negative and my model outputs something positive, it's going to be negative. So this will not hold true. And the other way, if it's positive and this one comes up negative, basically, if my prediction is wrong, then that will, or if there is a violator in my street, this is basically doing that. How that will make sense right over here. Here, like in this part and this part, we're trying to like get everything out of these margins. And by definition, these margins is where your function intersects at +1 and -1. So 0 over here. So if your function h is 0, so you're dealing with this line. +1 is this one, and -1 is this one. So that's the definition. So that's why he's using this equation over here. So, okay, so that is if you're using the hard rigid margins. Then we can also use soft margins. And how can we do that? He's introducing a slack variable. What slack variable is to the same thing as the C, similar to the same thing that we talked about C hyperparameter, but we are introducing it as how much of violators are we allowing to happen in our model. So the same thing as before. So we are trying to like decrease our weight with the same thing, but we are also adding another sum over here. And that is the same hyperparameter C that we had, defining our flexibility. And now the slack variable, a new one. So these will compete with each other. If one goes up, the other one is also goes up, the end, and this is like, we are trying to minimize the whole thing, right? If any of them goes up, it will add to the weight and it's gonna be terrible. So basically adding the C to this, it's not gonna let this one go crazy, or having this one not gonna let C go crazy. So, and then, okay, I thought somebody wanna talk.
Yeah, hi Alvira.
Yeah.
Thanks for the presentation, but I have to leave. So I'll join next time.
All right, thank you so much for staying up to now.
Thank
We're
you.
also
Bye.
doing a wrap up anyway. All right, thank you. All right, so I'm just going to continue. So here we're introducing slack variable over here. If it's 0, it's again, if the slack function, the flexibility is 0, it's going to be exactly the same as this one. But if it's higher number, it's gonna affect my function, basically. Now, these are the way that we are defining our, this is similar, like equivalent of when we define a loss function in regression, Abby, this is for that matter. If you're defining our loss function under regression models and we're trying to solve that, we're looking at that problem as an optimization problem. And to solve the optimization problem, one of the ways to do that is using gradient descent. There are other ways to do that, but gradient descent is the best of them. Apparently that can work on many of them. But here, this is our problem. And we're trying to minimize this when it's conditional to this one, okay? And apparently, this fits under quadratic programming problems. The other one was optimization problem, and probably this is one of those also, but this is called a quadratic programming problem. And here is the general formula for that. And because it just by looking at that, it's kind of similar to what we have over here, right? So these are general terms, and we can just change them and modify them in such a way that it can we can include our soft margin definition, slacks and all of those stuff, or just with my good old rigid margins, like over here. So this is how you solve it. I don't know how to solve it. It's difficult for me to understand the whole thing and like how you can just change this one to that one, but this is the concept of it. So this is a function in math and this is how they solve it. And they don't even like do it manually. So there are like some products out there that can do that for them. And going down, okay, now, so I didn't mention that before, but he's been talking about something like kernel trick. Remember we had the SVR or SVC, and we could have used a linear or like RBF or any kernel. So apparently kernels make them faster, and like how they do that mathematically is that, so again, these are not something that I'm very good at, but the thing is that apparently when you're trying to solve a problem, you're having a primer problem, then you can drive a dual problem based on that. If your data or whatever that you're dealing with fits some sort of some constraints, and that is under Mercer theorem, if you fit those conditions, you will be able to use a kernel system, and I'll tell you how. So remember, we wanted to transform our data, like we introduced nonlinearity problem solving with mapping our data to a transformed dimensions, and then dealing with them in that dimensions with a transform form. But apparently, you don't have to do that. You don't have to actually do the math and like transformation. Instead, you can do a trick, and that trick is that he's just solving that trick over here, meaning that, by the way, this phi is phi or phi. This is showing that if I, consider that a feature, A as a feature and B as a feature. And if you're transforming it, so we're adding a transformation function to that, if we get dot product of them, it's going to end up as if you didn't transform it. It's going to end up, so this one will end up as this one. What happened is that we didn't even have to do the transformation and do anything. If you get the dot product of them, it's just the same feature. So, but to be able to get from a transformation map to actual vectors that we initially wanted to transform and our data and like our model or whatever, it has to meet certain criteria, and those criteria are under Mercer. Those criteria are listed over here. Like I'm not sure what these are, but if those criteria are met, we can find a function that the dot product or our transformation will end up with the same vectors that we began with, the same features that we began with, and let's see. Okay, and then that's basically it. So we're not doing the actual work. We're just doing it kernel trick, and that function is the kernel itself. So what kernel is that, and these are like how you can turn a linear kernel, use linear, turn a polynomial, RF, or sigma. Okay. So, and then I don't understand these. If anybody does, please jump in and like explain it. And I probably is just doing that thing that I just summarized with my basic explanation. Now let's just move on to the last thing that is also important. For online SVM, we said that the SVC kernels and SVC linear, they don't do online, and they're not good at online things. So what he suggests to use, again, the gradient descent classifier to do the job for us. But now we're going back to the same thing. We're going back to the same loss function definition. And on this one, again, our loss function by definition is to reduce this, and also to add something to our loss function that is that will depict our goal not to let violators in our street for the classification problem. Okay, and this is that argument over here. So decrease the weight to get the largest street, and like define, add something, some variables, define some variables here that will give you less violators. And here, what this thing is over here, the function of maximum of 0 with, as opposed to 1 minus something. This something is what the whole thing, this is the hinge loss function, hinge loss, which is over here. So this is the graph for that. This is the maximum between 0 and 1 minus t. If t is 0, maximum of 1 and 0, it's obviously going to be, it's going to be 1. And so, or if this is, so in order to get 0, if this is like higher number, obviously it's going to pick 0 as the maximum of that. So this is like how it is. And this t is a function itself. And that function depends on my prediction, right? So by incorporating that loss function in my bigger loss function, and this is how it goes, linear SVM classifier loss function. And we're doing this to be able to use SDG class, like a gradient descent classifier on my SVM model. And yeah, and then that's it. So if anybody is interested, we can go through the exercises.
We can go to the exercises, but that was, I mean, let's just be honest. This was the best
Thank you.
book club. Not better than other people, like just everyone. This was fantastic. You know, yeah, this was great. I think you actually tackled all these questions through your discussion. I want to give some time for Nazanin, who hasn't said a single word. Are you still there, Nazanin?
Yes, I really enjoyed this chapter, and thank you, Elmira. It was fantastic. Thank you.
Thank you.
Yeah. I mean, I don't want to take any. This was just perfect the way it was. I don't want to go back and start. And so, could you share your slides onto the Slack?
Absolutely. I'm just going to put it on the Slack channel.
Yeah, Slack channel. Abby, what did you think?
a great job of explaining everything in terms that like I understand and kind of like relate to. I don't know, because when I read, I kind of especially I had question mark about the last part of the under the hood and the quadratic programming and stuff like that. And the way she explained the math, I like it. At least I understand a little bit better what we were doing, getting the last part of the equation for the hinge and that W transpose to W, the vector. Yeah. Thank you, Amir. You did a great job.
Toby.
It was a shattering glass ceiling experience for me. Omira did, she was so fantastic with her presentation, and the best part for me was the kernel trick. And from what I read initially, and when she presented, I had much more clarity. Thank you, Amira.
Yeah, I mean, this is just perfect. Even I learned quite a bit, actually. I didn't spend too much time on the math because I also got a headache. But now I can go back and read and explain it exactly. And also the fact, your strategy of going back to show what's the bigger picture again, like these are the data sets, these are what we've learned, I thought was super, super helpful. Because, sometimes even if someone was new today, I mean, I don't know about Leila's experience because she had to go, but even if they were new, they could at least learn something, because it wasn't just like jumping. So I thought the format and going back and which is something I don't do during the presentation. So one thing that's grown out of this last 3 weeks from Toby, 4 weeks Toby, then Chima, then you, is this idea that if you make a presentation that's followable, I think it helps with the understanding, in my opinion, But I mean, Toby, I interrupted you, sorry.
No, you didn't. I'm done.
Okay, this is a very high bar. Who's going to do decision trees, right? I think that's the next one, right, Amira?
Yeah. Yeah, decision tree. And just by the way it says it, it's just 20 minutes. So one thing, let me just tell you this. Like SVM, like compared to what other people had to do, like with training models that Chima had to do in like 2 sessions, it's just a lot less content to cover. So I was lucky to begin with. And but that's another factor. So I also built my stuff based on what we learned. If you don't know anything, you can like go back to anything. So I was lucky to jump into chapter 5. So I was also lucky.
But I said this was perfect, better than Judy, everyone, but that's not to discourage anyone. I thought this is not what I envisioned for this journal club when I started.
No, what I'm thinking is that we're so when we first started, like we are basically building based on the feedbacks. So you started, and then Toby, you gave us classification, the MNIST, you did that, and then Chima came in, and then basically we're building. So whatever comes after me is going to be even better because we are building on top of what the feedbacks that we are getting. It's not that me or other people, it's just the way that it's incrementally we're getting better as a group, I guess.
I agree. Decision trees.
Any taker?
It won't be bad. Okay, Toby, I'll volunteer you then. Is that okay?
Yes,
But
it's fine.
and guys, don't feel like you have to attend every weekend. Seriously, you should still like, you can be like, oh, I don't want to do it today. And if we get to a point where you want us to take a break, I'm okay with that too. We can just, this is like supposed to be less stress. That's why we record this. You can play through the car. This was very, very good. So if you look where we are, so in decision trees next week, which should be done, then ensemble, learning, and random forest. and then dimensionality. And really by chapter 8, we should have done supervised learning. So you should be able, not necessarily that you're using deep learning, but you're using supervised learning to do routine machine learning projects, okay? So we should have more of like show and tell sessions where people just come in and show what they did, and then we can move on from there. And then so the one thing so if we can get there, then the next one is unsupervised learning, and then we go to deep learning, you know. And so because I think reinforcement learning comes like on chapter 15. Yeah. And trust me, it's going to be crazy, but I think it's going to be something a little even easier with deep learning, with the basics we are getting. I mean, Nazanin writes a lot of deep learning code. I know Toby is starting to do that. But do you think that you're learning something, both of you?
Yes, yes. This book is really amazing, and I think if I want to read it alone, it was really hard to understand some of the parts. But now it is much easier, and I learn lots of things. And I want to actually, because I didn't talk, and I didn't choose any chapter to explain, but because I'm busy these days, but I want to explain the neural networks and deep learning chapter.
Okay, works for me. That's even better. So that's the other. So the neural networks one is just more of a section, right? Because then that will be chapter 10, right? So if you see, that's like 1 minute. So do you want to do introduction to artificial neural networks, or training neural networks, or custom models?
Yes.
Yeah. So you can pick one of them and let us know, okay?
Okay, sure.
Yeah, and I mean, really, if anyone wants to pick something, I just don't want to speak because I don't think I'd have done such a better job than all of you, because I agree with Elmira. We keep getting better with every week because we're giving feedback, okay? And so, yeah.
One thing that I was thinking, just to because I have the exam coming up in February, and I'm just trying to see how many of chapters I will be missing.
Yeah.
So just looking at this, so this what you've done so far, we had to like break down some of these chapters. This the California thing, we had to break it down because I have some understanding of based on the minutes that he's put here. So that was a long chapter, and also like the training model, we did it in two sets, and that was a long chapter too. Decision tree will be done in one chapter. Probably the random forest will be done in one chapter. The same for H2. Maybe we have to like spend some more time on maybe two for unsupervised learning. So 1, 2, 3, 4, 5. So before neural networks, we have 5 weeks to go. And I hope I'll be at least I'll attend like 7. I guess I'm hoping to like at least attend some of them before if I go to exam mode. But and then after that, in 3 months, probably you will be in 1 month you will get, in 2 months, let's say, we will be at neural network, and then at starting the neural and these are like hard. So I don't think that we can handle them if we don't learn if you don't go through the chapters beforehand. I don't think that we can put them just in 1 week. So maybe it's gonna like take all the way to let's say we have almost like 10 of them, maybe like
2 weeks.
Yeah.
5 months. And I don't want to rush, by the way. I would like for you, before you go, to be up to number 8 at least, because I think if you skip unsupervised, it's gonna be fine.
Yeah.
You know, like you won't be completely lost.
Yeah.
You know, when you come back. And honestly, when you come back, if you want us to repeat, we'll repeat it.
Oh no, no worries. Like what I will do is I will go through the chapters.
Oh, you're gonna
don't worry.
prepare
I will. Yeah. I will go
Oh,
through the
you're good.
chapters and I'll ask you my questions. Don't worry about that part.
Yeah. So yeah, and I think that so what I want to do, and this is what I was saying, I give that presentation beforehand, is to allow us to start now immersing ourselves, right? You guys can see we've learned quite a bit, right? But, and I'm glad, like Abby's like, oh, I read this and was like, oh, ROC, I know what this is, you know? AU ROC, I know what this is. And even in Monday lab meeting, you'll hear me ping you and as an Toby and as a name, like, oh, you should understand what Imon is saying, right? Now, so what we need to do is a little more, you know, experiments and experience. And so I do want to see a lot more activity with that. Nazanin, you should be having a blog by now. Toby, you should be having a blog by now, you know? So I want to see a little more movement on those things, okay?
Sure.
Yeah, okay. Abby too, you should be having a blog. And I'm very encouraged that you listen to me and are still with us. So that's
Thank you. I'm excited to be here. Every week I'm learning something new, and even though sometimes like I find it goes over my head, I go back and I read, and all of the explanations like they stick out to my mind. And then when I read some things, I'm like, oh yeah, that's what she meant.
yeah,
Oh, okay.
exactly.
So it's a slow progress, but I can honestly say that I'm making progress and I'm enjoying myself.
Awesome. That's amazing. Okay, final word. Toby, you okay? You safe out
Yes, I
there?
am.
Okay.
Thank you.
Okay. Abby, finally, before they kick you out of Starbucks.
I'm doing good. I'm safe out here. Yeah.
Okay, make sure you vote. And Nazanin, you safe? You still awake? I know it's late for you.
Yes, it's okay.
Okay, awesome. And I'll reach out to you about the meeting to review your work, okay? And I'm doing good. Judy's doing good. Very happy to, I love doing this. By the way, I didn't think I'd enjoy it this much. I'll keep trying to bring more experiment to tie things home. Repetition, repetition, repetition. And Elmira, you have the final word. Again, fantastic job today.
Thank you. Like, one thing that I've learned, not just for this one, at first I felt like, okay, everybody knows, and I'm just gonna be explaining stuff that everybody knows, but having this feedback is really good from people who actually, these things are just basics for them. Like, I know that it is, it was good, encouraging, thank you. And I think that the best way to learn is when you're trying to explain it to someone, and that works for me at least. So that was great for me. Thank you.
Awesome. Okay, team. Bye. Have a good week.
Thank
Stay
you.
safe out there. A bigger surge for COVID. Okay. In the US. So stay safe out there. Okay.
Yeah.
Bye.
Thank you. Bye.
Bye.
Thank you.